Hi, everybody. I'm Pavan Turaga from Arizona State University. Thank you so much for inviting me for this presentation. My talk is titled Topological Methods in Modeling Human Activity. Thank you so much, organizers, and I hope my talk blends well with the rest of the offerings. I'd like to make a special emphasis on modeling human activity as it applies to perceptual robotics types of applications, which is recognition of human activity, understanding qualities of human activity, and what does topology have to offer, and maybe geometric methods also. Before I begin my talk, I wanted to outlay a few high-level pointers about how I think about human activity and why it is really difficult to come up with a comprehensive framework that addresses human activity. If you try to define what is human activity, it's nearly impossible. It's nearly everything humans do. It's human activity. Going to your store is human activity. Driving is human activity. Breathing is human activity. Sleeping is human activity. So where do we draw the boundaries? At some point, the boundaries are drawn by the sensors that you have. Can you record evidence of the activity of interest through the sensing mechanism that is available to you? And therefore, in different communities, people talk of different categories of human activities depending upon what sensing modality is available for them. In perceptual robotics, typically we talk about video-based sensors, maybe depth sensors once in a while. My work expands beyond video and depth sensors. I also talk about wearable devices, human activity that is sensible by pressure platforms. So all that stuff is not part of this talk, but when I refer to human activity, I tend to take a very expansive view, and it's the choice of the sensor that often helps me narrow down the scope of what I mean by human activity. Here is a very quick visual. In addition to what a sensing modality affords you, there is also a broad categorization of the complexity of human activities, which is generally recognized in the field. You may have human activities, which is defined by the activity of a single person, spatially localized, like throwing this ball, throwing this shot put, spatially localized, and also temporally small, spatially temporally localized, if you will. And then if you expand the space and time dimensions, spatially distributed or temporally distributed, you start getting more and more complex activities as illustrated here. If you start talking about activities that are done by groups of humans in coordination with each other, that adds a whole other level of complexity. For the purposes of this talk, when I mean human activity, I broadly constrain myself to the simplest categories of actions, which are single human, spatially and temporally localized. So that's where most of our explorations have been in applying topological methods. And even that has been challenging, but we've had some initial successes and not successes. So I'll present the whole story. So why is modeling human activity hard? I've already kind of provided a hint to you, which is it's first of all very hard to define human activity objectively. You have to define it in terms of what is available for you to sense and what is the complexity of the activity that presents itself. In addition to the problems with sensing and the difficulty of defining human activities, it is also there are very many confounding variables. And confounding variables, there is no shortage of confounding variables. In the computer vision community, people talk of semantic variability, and this often applies to complex activities which involve interactions with objects, multiple people in the scene, activities at a bank, activities in in large organizations. Those are semantically highly variable. When we talk of single human activities, spatiotemporally localized, we still have lots of variability depending upon sensing modality. If it's a camera, if it's sensing a single human in the scene, what's the viewing angle? That leads to measurement variability. You're taking a snapshot of the same phenomena from a different angle, leads to differences in measurement. If it's a wearable device, same thing. Which part of the body did you attach the sensor to? That leads to variability in measurement again, and so on and so forth. There's all these choices of sensors that lead to measurement variability of the same phenomena. The same activity could be sensed through multimodal means. Video is one, audio is one, wearable devices are one, and there's no dearth of sensors, which are now called privacy preserving sensors, EM-based sensors, and radar-based sensing techniques. All of these are being talked about in the context of human activity. And we would like a framework that is at least broad enough that encompasses many of these variables, and hopefully we don't have to invent new methods for everything. That's the hope. And human activity by itself doesn't tell us what we want to do with it. Human activity recognition is a common application, but it is not the only application. People talk about human quality assessment, movement quality assessment, which is often of critical importance in skill-based tasks, surgical skill assessment, or movement assessment in physical rehabilitation tasks. And more and more so, people are interested in modeling qualitative aspects of human movement for humanoid robotics. How do you make a humanoid robot move more like a human being with all its nuance, with all its gestural fluidity? So what is that quality that we are lacking? So all these are the broad spectrum of applications. In this talk, we will take the simpler version of the problem, which is single human. The sensing modality is probably going to be a camera, maybe motion capture, spatially and temporally localized. We are interested either in recognition or in quality assessment, and we shall see how far we can push the boundaries with newer methods from geometry and topology. One of the common ways in which I have tried to motivate most of the work that I do in this area is through interpreting human activity as a dynamical process, which has a lot of precedent. I mean, I'm not the first person to say that. There is a lot of precedent in thinking of human activity as defined by a dynamical system. In the good old days, people would talk about dynamical systems as defined by parametric forms like hidden Markov models, linear dynamic systems, switching linear dynamic systems, coupled hidden Markov models. The variations are numerous. And the recent success in applying dynamical neural nets like LSTMs, recurrent neural nets, and that whole variation of techniques also lends credence to the idea that human activity can be thought of as a dynamical process. Of course, the classic issues are: what is the state space? What's the observation space? Where is the dynamics? How do you define these things? These are the classic problems. One of the ways in which we have tried to move away from this problem of defining and identifying model parameters is to try and think of them as through the non-parametric lens, through in ways that has been referred to in many different ways, including chaos theory, ways of thinking about dynamical systems. So those of you who are familiar with nonlinear dynamics will find this tutorialish example simple. For those of you who don't, what you're seeing is a simple differential equation in 3 dimensions written down here. These are the equations, and this is the Lorentz attractor. Typically, we think of human activity also as being definable. Stable, quasi-periodic human actions like walking can be defined by simple dynamical equations, and the art exists in defining those linear equations. I mean, coupled non-linear equations. If you did a good job of it, you can use them to synthesize human activities, like in graphics. But if you don't want to get into the weeds about defining human actions with equations, what can you do with observations? The theory of nonlinear dynamics says that even if you have a well-defined partial differential equation that models human activity, if we were to take measurements of the human activity from observation dimensions, you get time series which on the surface looks chaotic, and that's why they use the word chaos theory here, but nothing is really chaotic in the popular sense of the term. It just means that human activity will exhibit a lot of variability at the signal level, depending upon how you're measuring it, depending upon which phase of the movement you start measuring it. How you're measuring human activity is a direct connection to how you're sensing human activity. And it leads back to that choice. The same 3D movement, assuming it's defined by or governed by some nice dynamical equations, measured from different angles is what the measurement variability is, will lead to very large diversity in the measured signal statistics. The same human activity measured through a wearable device, but now attached at different parts of the body, will lead to very large variability in the observed signal statistics. The same 3D model, the same 3D activity, depending upon which phase of the movement you start recording, even if you choose the sensor, video, same view, you fix the viewpoint and the sensor, but now the variability is which phase of the movement did you start recording in, will again lead to a large variability in the observed signal statistics. So all these empirical observations are explainable through the lens of dynamical systems, and therefore there is something to be said about thinking through modeling human activity through dynamical systems. The trouble with the nonlinear ways of thinking about dynamical systems, and through asking this question, what can you derive from the measurements themselves without making any assumptions about the generative process, leads us to topological methods. So here is an example. Here is the same Rossler system. I mean, so the Lorentz attractor, the Lorentz system of equations. When you tap into one of the dimensions of the observation, and you adopt a process known as time delay embeddings, which is due to a very famous theorem due to Takens, Floris Takens, back in the 80s, proved a very nice theorem that said, under certain assumptions of the generative process being smooth and reversible and things like that, and all the variables being entangled with each other, then when you make these observations of the dynamic system through individual dimensions, you can recover an a rough topological equivalent representation of the dynamical state space through a process called time delay embeddings. And the keyword here is time delay embeddings is simple. You take the signal, you delay it by a few times, you vectorize the signal through concatenating delayed versions of itself, and then you just let it evolve in this concatenated vector space. And what you will see is a time series evolving, which looks qualitatively similar to the true evolution. If you have this bimodal, this double butterfly-shaped, form occurring in the true state space, you will see something similar occurring in this time delay space, except you're not guaranteed a Euclidean reconstruction. You're guaranteed only a topologically equivalent reconstruction, which means things could be bent and rotated and twisted and all that stuff can happen, but it would still qualitatively have the same numbers of lobes, the same number of holes, and things like that. So this is where the beginnings of topology or topological data analysis methods are for human activity modeling problems. Which means if we want to extract invariants, qualitatively, we talk of topological invariants as features, measures, what have you, that are invariant to this shearing effect, this bending and stretching effect. If you followed the field of topological data analysis, lots and lots of methods available now to create things like features like persistence barcodes, persistence homological features, persistence diagrams. And I can't provide a tutorial on those things now, but hopefully through the course of these talks, you have heard these things spoken about before. We'd like to see how they apply, how they perform in practice when applied to real data sets in human activity. So here is a very quick diagram, one slide overview of what topological methods are. If you have a bunch of points in a metric space, and where are these points coming from in our situation? In our situation, these points come from recovering a topologically equivalent dynamical phase space through time delay embeddings of certain measurements. Now, these measurements can be, if it's a camera, I'll talk about what we measure, what features there are. If it's a time series from a wearable, different measurements. If it's motion capture, different measurements. So the input measurements are different depending upon the sensor. But after that, we follow a roughly similar process in recovering one of these phase spaces. And so this point cloud resides potentially in high dimensions. It's not going to be 2D and 3D. It's going to be much, much higher dimension. But from there, we hope to extract features that are invariant to the intrinsic topological equivalence that exists in this process. And we hope to get persistence diagrams which encode the birth and death of significant topological features like cycles, voids, connected components, and so on and so forth. And of course, most of these things were due to the advances of Herbert Edels-Brunner, Gunnar Carlson, and that whole lineage of mathematicians. I will spare you this single slide tutorial-ish introduction to TDA. I'm trying to also make sure we have time for, I want to keep to my time. So here is a very simple example of how we find TDA features working for real human movement data captured from motion capture devices. So on this bottom left panel, what you're seeing is time series data from a motion capture experiment involving reaching actions Okay, reaching actions, I'm sorry, this is synthetic data extracted from one of these standard attractors, and we will soon see how this works for real data. So this is time series data from one of the dimensions of the Lorentz and the Rossler attractor, and recoveries of those two attractors through time delay embeddings and its topological features computed in terms of persistence diagrams. We see that there is some noisy features, which are the points near the diagonals, but then the two major lobes, the two major holes, are available as significant features in this case as well as in this case. There is this one significant hole that appears, one significant cycle. So in terms of applications to human activity analysis, here is what we were able to do for a motion capture data set, which consisted of 5 different actions: dance, jump, run, sit, walk. This is from a data set that was available from a few years ago from one of the motion capture studios in California, but it was also made public. Recognizing human activity from motion capture has a history. We wanted to see how these methods do compared to some of the other state-of-the-art methods from a few years ago. And this is slightly pre-deep learning. We have been beginning to fuse these things with deep learning, but it's relatively newer work, but this provides us credence that these things actually work. We were able to extract very simple shape-related features from these kinds of point clouds, and these shape features were motivated by what people have used in graphics communities, including things like shape distributions. Using shape distributions as a feature to represent this leads to fairly high performance already. But then using persistence diagrams and using Wasserstein metrics on persistence diagrams really bumps up the performance to extremely high levels of accuracy. So that was interesting to see. We wanted to apply similar things to a stroke rehabilitation application. So here is a video of a motion capture session for someone who had suffered stroke. And we have all these motion capture markers attached to the body. We are looking at the wrist and how its movement is when you reach out to grasp an object. I'll try to share the video. You may not get the audio clearly, but you will see the person trying to reach for an object on the table. And the manner in which they reach indicates different kinds of deficits, and it informs the therapist's protocol that they want to apply for this person going forward. So one of the classic questions in this space, in the physical rehab space, is to measure the quality of the movement in a way that at least correlates significantly with the therapist's impressions of the quality. What we did was very similar to what we did for the activity recognition experiment. We would take time series from the wrist, XYZ locations of motion capture data, treat each dimension separately, do this delay embedding thing, recover an attractor, describe its shape properties, either through shape distributions or through topological methods, and then use that feature to build a regression function that would map it to a therapist interpretable score. And very quickly, we found that this holistic way of thinking about human movement through dynamical systems lenses really bumped up performance. And we were competing with methods that use like nearly 30 different features extracted from the wrist, the elbow, the shoulder, the torso, treated differently, independently, and then fused in some very suboptimal ways. Compared to that way of doing things, even just the wrist, we know that all the joints are entangled in the reaching movement. So potentially, you should be able to get all the information about the movement quality from just the wrist if you treat it as a low-dimensional observation from this coupled dynamical system, and we were sort of corroborating that. We found that using just the wrist, we got a very high correlation coefficient, 0.85. But then when you treated each of the joints independently and extracted different features for each joint and then fused them, you do get a higher number, but this is using 14 different markers at 14 different locations on the body. So the dynamical systems ways of thinking will help us reduce the need for marking up the body and reduce it to just a single joint. This is something we showed in 2015 and 16. We have an ongoing collaboration with several stroke therapists funded through the NIH. We have faculty in Virginia Tech and Emory doing this kind of work. And this study really helped us to show them that you don't need a very expensive motion capture setup. Somehow just get the wrist and we can figure things out from there. And that's what we're doing now. So most of our home-based stroke therapy protocols we're involved in use only the wrist. How does this work for video? In video, we have other choices to make. In video, the measurements, we have the 3D space. We have confounding variables, which are even more difficult. We have clothing. We have lighting conditions, we have texturing, we have body type, body shape, all these things which change the measured features in addition to simply the viewpoint. The viewpoint of a camera is one of the confounding variables, but there are many more. So going into the problem of describing human activity as a dynamical system that is being reconstructed from observed video feeds from different views is already challenging because the variability is way beyond just the viewpoint. The variability involves body shape type, the clothing you wear, the lighting around you, all those things which we can't really account for. But still we went ahead and trying to define human activity as a maybe a dynamical system that we can define in high dimensional feature spaces. So how do we get to a high dimensional feature space? Some design choices have to be made. Do we go and extract features from each individual camera and then do time delay embeddings from it? That's one way to do it. Or can we extract features from each frame of the video and then treat the feature evolution in the feature space itself as a realization of the dynamical system? That will actually work okay because we are already in fairly high dimensions through features. You don't quite need to do time delay embeddings to get those higher degrees of dynamics resolve. Sometimes you can avoid time delay embeddings if your observations are already high dimensional. And in our case, in the context of video, we already have a high dimensional observation. So we can, in some cases, avoid time delay embeddings. That's what we tried. So we would take each frame of the video, extract simple features from it, like histograms of gradients, time series of histograms of gradients, already high dimensions, probably thousands of dimensions already, and then treat that feature space evolution as the point cloud that's given to us from which we extract topological descriptors. So already we found just doing this much. Take video frames, extract histograms of gradients, create a time series of that, embed that and treat that as the feature space or the point cloud that's given to you in that metric space, and then do TDA on that space. We start getting these really nice persistence homology descriptors, which we found are already fairly robust to viewpoint and discriminative across activities. So the first column is one action check watch from three widely different views and look at the persistence homological features. They all look kind of similar to each other and relatively different, quite significantly different from, let's say, a sitting action and a walking action. So this was very interesting for us to see that looks like topological features could work on high dimensional features derived from images and videos, even though there are all these other confounding variables like lighting and clothing and all that stuff. But again, as I mentioned, there are other confounding variables beyond just viewpoint, so we don't quite know how to tackle those yet. We hope that the features we extract, like HOG, provides us some robustness, but it's not 100% robust. So despite extracting these features, we found in experiments that it's by itself not enough. The topological features seem to exhibit this, shifting of points depending upon how you extract them. So like here, you can see that the points are somewhat stable, but they're a bit noisy. There is some noise. We don't quite have a good handle on what is a noise model that would describe that shift. You would have to be very analytic to get to that. We took an engineering approach. We said, let's take the persistence diagram that we have and sort of artificially perturb it a little bit to provide that robustness to perturbations, and then collapse that whole stack of persistence diagrams into a subspace. Before we compute the subspace, we sort of convert these PDs from multi-set of points, from this discrete multi-set of points, to a more continuous representation using things like persistence images. We think of, the way we used it is we basically put a little Gaussian on each of these points, and what we have, you can call this a persistence image, or you can also call this a kernel density estimate of these points on this 2D grid. That's how we think about it. It is intuitively satisfying for me to think of each of these as a kernel density estimate of an underlying distribution, because that immediately helps me think of these as points on a probability simplex or a probability hyperspherical manifold and through some square root forms. So it's already giving me a geometric intuition in how I define metrics on this space. In addition to that, when we are doing this perturbation, we further collapse all these functions, these KDE estimates, into a single estimate through simple PCA. So take all these maps, think of them as heat maps, collapse all these perturbed heat maps into a single representation through PCA, through a subspace. And that embeds this whole stack of perturbed PDs onto a Grassmannian manifold on which we know how to define metrics and measures and statistics. And we use that as a measure of, as a divergence measure between these two videos. And from there, you can do machine learning. You can define kernels on the Grassmannian, you can define PDFs on the Grassmannian, you can do any classic machine learning method on the Grassmannian through this embedding. We were also able to prove some stability results, that this embedding and the metric that we inherit from the Grassmannian is actually stable with respect to, Wasserstein metrics. So that was also intuitively satisfying. Before we show you results, we wanted to do a sanity check on that these things actually kind of work okay on carefully constructed data sets like basic 3D shapes before we start doing videos and all that. At the core of what we're doing, even though we're applying all these things to human activities, at the core of what we just showed you is really just a new metric on topological persistence diagrams, which is robust to topological noise. Which is robust to noise in the basic point cloud, which is arrived at through this perturbation process and through collapsing things to a single subspace and then using Grassmannian metrics. This can apply to any application of TDA where you have a noisy point cloud to begin with. So our initial tests were, if we start with simple 3D shapes and then we make them noisy through adding noise on the shape, and then how do our topological descriptors perform? Initial experiments said we performed really well under fairly large perturbations of noise and extremely fast. So we are replacing the gold standard L1 Wasserstein measures and all those combinatorial problems with a simple geometric problem on the Grassmannian, which is classically analytically solvable. We find that we are able to recognize shapes under large perturbations under noise. Here is increasing noise severity on this axis. The bottom two rows are our approaches on using perturbed topological signatures as a way to measure divergences between shapes. Extremely robust to noise and extremely fast. The other classic gold standards are, the one Wasserstein measure, the two Wasserstein measure, the bottleneck distance. Also robust, arguably less robust than us, but it's fairly robust, but they are extremely slow. And this was a big thing I thought we would contribute to the community. And I'll move on. And then how does this work to in the applications to video? So we found that perturbed topological signatures, or even just perturbed, or even just classic L1 Wasserstein measures by themselves applied to this hog features is not particularly good. So we had to do a lot of feature fusion. We had to work with histograms of gradients. We had to work with other features, including optical flow features, and then do similar things across different feature modalities. And when we did a lot of fusion of these methods, then things started improving. However, we are still not 100% sure that this is, we have good belief that this is going to give us strong robustness to viewpoint variations, but because the other variables are unaccounted for, we still don't quite have a fully end-to-end system that we can provide some very strong guarantees on performance. We are beginning to work with fusion of these methods with deep learning features, which will probably provide us some robustness to simple things like translations, registration errors, lighting conditions, clothing. Deep features are robust to those things. Deep features are not known to be robust to viewpoint. So the fusion of deep features with topological representations could be promising. We haven't yet done that work, and we are hoping to do this in the future. One of the recent successes, implicit successes, not us, but a team which was completely unconnected to us, used our method, and they won the first place at ICLR 2021 on computational geometry and topology. So they used perturbed topological signatures and our metrics to be the best performing submission to this competition. So that's great validation, third-party validation. We got nothing to do with them. That was satisfying. So where are we headed next with this? So as I kind of hinted, we are trying to connect these things up with deep learning a little more deliberately. We are looking at 2 or 3 different ways of doing the connection. One is, yes, we could use deep learning features. We can tap features from some deep net that is trained for image recognition, apply that frame by frame on video features, and then treat that sequence of features as a point cloud in a metric space, and then start thinking of topological features derived from that. That's one way to go about it. The other angle we're taking is can we attach topological features can we append it directly to deep features and let the DeepNet do the fusion optimally? The third angle is, can we use the DeepNet itself to speed up computation of topological features? And if topological features can be learned, then that fusion with other deep features could be more optimal. But all of this is somewhat speculative at this point. I won't make a conclusive statement any which way. And hopefully we'll have a conversation that might help me figure out which direction to head in. But one of the things we published last year is this initial idea that maybe topological features can be learned under certain very special conditions. Uh, as applied to images and videos, there is a very specific way in which we talk about topological features. We either talk of topology of the height function of the image, and then we can try to regress for limited databases the topological features constructed through thinking of them as these height functions through deep nets. We have been finding good success in doing that, but I would like to hold off making a conclusive statement on how we want to use it. And I'm happy to, and lots of applications to other time series data as well, but I'd like to conclude my talk at this point of time in the interest of time. So in conclusion, what we are doing is we are thinking of topological methods as applied to video and human activity as a way to provide robustness to confounding variables like viewpoint changes and measurement variability associated with things like variables. Where in the body do you attach it? The entry point is to think of human activity as dynamical process from which these sensors are taking low dimensional observations. Because of that, there is math that tells us that whatever you can get through such a framing is a topologically equivalent version of the true state space, and therefore topological methods are a natural candidate. But they suffer through things like, are they robust to noise? Are they fast enough? And we have made some headway in making them robust to noise and making them super quick through geometric metrics like metrics on the Grassmannian. We're beginning to ask questions of fusion with deep nets, and I'll be happy to take your advice and steer that boat from there. Thank you so much. I appreciate the opportunity, and thank you so much for the organizers for inviting me. I'll be happy to be around for conversation and discussion. Thank you so much.